So today we're going to be covering rationals. We're going to be looking at simplifying rationals and also graphing rationals. So remember, when we're looking at a rational, we're talking about a rational function. So hopefully we remember back that a rational number is something that can be written as a fraction. So like 0.25 I can rewrite as 1/4. So that is a rational number. The square root of 7 is an irrational number because I cannot write it as a fraction. So for rational functions, it is going to be a function that can be written as n of x divided by d of x where n of x and d of x are polynomials. And we've talked quite a bit about polynomials and what our polynomials look like and all of those sorts of things. And so now basically we're looking at two polynomials that are being divided by each other. All right, so it says, find the domain of the reciprocal function f of x equals 1 divided by x and discuss the behavior of f near any excluded x values. Now, so the first thing we want to look at is our domain. And so notice that it asks us to first look at any excluded x values. And so hopefully we recall that when we have a rational function, our denominator is not allowed to equal 0. So because we just have x in this case, we know that the domain is going to be all x such that x cannot equal 0. Now, it can be anything else besides that. It just can't be 0. And then it asks us to look at values near the excluded value, which is 0. Now, near is a little vague, so let's look at a few numbers. So, if we say started with 1, well, 1 is near 0, so if we plugged in 1, so let's make a table. We have x's, we have y's. If we plugged in 1, notice we would have 1 divided by 1, so we would get 1. Now, let's think about that. Like, 1 is kind of near 0, but can we get closer? Yeah, we could plug in something, say, like 0.5. Now notice if we plug in 0.5, we would get 2. And again, we want to think, can we get closer? And the answer is yes. So let's say we wanted to plug in 0.1. In that case, we would get 10. Well, can we get closer? Well, yes. If we plugged in 0.01, we would get 100. And so it's going to continue in that same pattern. We can get closer and closer and closer and closer. And notice, so as my x values are getting closer towards 0, notice that my y values are going up towards positive infinity. And remember that it just said values near 0, which all of our values are near 0. We got pretty much as close, and we kind of found our pattern. The only problem or thing that we need to think about as well, though, is that all of those numbers are going to be on the right side of 0. But if we think about it, notice that we would also have numbers that are on the left side that are near or close to 0. So we'd want to look at those behaviors as well. So likewise, if I plug in -1, I'm going to get -1. If we plug in a negative 0.5, I'm going to get a -2. If we plug in negative 0.1, we're going to get -10, and negative 0.01, we would get -100. So notice that our pattern is very similar. On my left side, as my values go towards 0, notice that on the right side, our values are still, like the number value is still getting bigger and bigger and bigger. But because there's a negative in front, those values are technically getting smaller and smaller and smaller, or more and more and more negative. So this time my y values are going towards negative infinity. And so hopefully we recall that this behavior, when we can get closer and closer and closer and closer to something, but can never quite reach it, is called an asymptote. And we have 2 main types of asymptotes. We're going to look at a third a little bit later on. But the first 2 that we're going to look at are vertical asymptotes and horizontal asymptotes. So remember that a vertical asymptote is going to be the line x equals a such that f of x goes towards, so instead of writing out goes towards, I'm going to draw a little arrow, so that stands for goes towards positive or negative infinity, as x, again using that arrow, goes towards a. Now the goes towards is basically a shorthand way of saying is getting closer and closer and closer to. We don't have a better way of describing that relationship besides just saying that it's getting close to it. As you continue on in mathematics, you will get better math to kind of describe that. But as of right now, that is the best definition that we can kind of look at. So remember that our vertical asymptotes are going to be vertical lines, so that's why it's x equals a number. But we also have horizontal asymptotes, and so those are going to be very similar concept, but it's going to be the line y equals a this time, such that x goes towards positive or negative infinity as y goes towards a. So again, very similar concept, but we're just looking at something that's horizontal or going from left to right this time, instead of going up and down. And I like to use kind of the picture of a black hole to represent asymptotes, because I think it's a good visual or thing for us to think about, that black holes in space, we can get closer and closer and closer, and everything's going to get sucked into that black hole. But technically, you never reach, right, the center of a black hole, because there's not a center of it. Same thing with asymptotes. We can get infinitely close to it, and our graph is going to get sucked closer and closer and closer to it, but we will never quite reach it. So let's look at some examples. So notice on our first one, we have both a horizontal and a vertical asymptote. We have a vertical asymptote at x equals -1 and a horizontal asymptote at y equals 2. Now our graphs aren't getting super close, but we've also condensed the graph. So if we were to zoom out on this, you would see this top part kind of going towards that vertical line, the bottom part going towards the bottom part of the vertical line, and both sides getting closer and closer to that horizontal line. Okay. So on this one, next one, we don't have a vertical asymptote, but we still have a horizontal asymptote, and this time it's going to be at y equals 0. And again, we're zoomed in, so it's not getting super close, but if we were to zoom out, those two ends would be getting closer and closer to our x-axis, but never quite reaching. And then on our last one, we have a vertical asymptote at 1 and a horizontal asymptote at y equals 0. So that's kind of what we're looking at when we're looking at our asymptotes. Now, let's remember how we find asymptotes. So remember that when I'm talking about a function, we talked about that if I have f of x equals, we're going to say it's n of x divided by d of x. And hopefully we recognize that n stands for numerator and d stands for denominator. So remember that our vertical asymptotes are pretty straightforward. Our vertical asymptotes are going to be any x such that d of x equals 0. Basically, any x value that makes our denominator 0 is going to give us a vertical asymptote. So we can set our denominator equal to 0, solve, and then those are going to be all of our vertical asymptotes. Now, the horizontal asymptotes are not as straightforward. Now, they're not like difficult, they're just not as straightforward. So we're going to need to do a little bit first. So let's say let little n be the degree of n of x, and little d be the degree of d of x. So basically, we're going to have three different options. Our first option is going to be if n, or the degree of the top, is less than the degree of the bottom, our horizontal asymptote is going to be y equals 0. Now, our second option, obviously, if it's reversed, if our numerator's degree is greater than our denominator's degree, there is no horizontal asymptote. Okay? And then obviously, hopefully, we can think about that our third option is going to be if those two degrees are equal. So what we do for that one, it's still, remember, because it's horizontal, it's going to be a y equals, and it's going to be the leading coefficient of n of x divided by the leading coefficient of d of x. So basically, we're just going to look at those first terms and just at the coefficients, and then we're going to divide them, and that's going to be what our y equals. So let's go ahead and look at some examples and find some. So when we're finding asymptotes or graphing, we have a couple of guidelines. Now, they listed out with a lot of words, and so I like to kind of come up with a little acronym that helps us to remember what we're looking for a little bit easier. So it says let f of x equal n of x divided by d of x, where n and d are polynomials. Same thing that we've been looking for. Our first thing is we want to simplify if possible. Next, we want to find and plot the y-intercepts. And then the next one, we want to find the zeros, or in other words, the x-intercepts. Our next thing is we want to find the zeros of the denominator, which are going to give us the vertical asymptotes. Then we want to find our horizontal asymptotes by looking at the degrees. Then we want to plot at least one point between and beyond each x-intercept and vertical asymptote. And then we will connect everything together. So I like to say our first step is going to be to factor and reduce. Now we won't always have to or be able to factor or reduce, but when we can, we want to. Our next step is to find the intercepts, and that's both sets, our y-intercepts and our x-intercepts. Then we're going to look for our asymptotes, and that's both our vertical and our horizontal. And then our last step is to make a table of points. And we'll look at how we pick those points here in just a second. So notice if I look at just the first letters, I have F, I, A, T, or Fiat. Like the car. Again, doesn't mean anything besides it's a way for us to kind of remember and make sure that we do all of our steps. Now, there are quite a few steps when we're graphing, and so that's why it's important for us to make sure that we find each of those components every single time that we do it. So we want to look at this example where we need to kind of put all of those things that we've been talking about together. So remember that our first step is to factor and reduce. Now notice 2x minus 1 and x are both already in reduced forms. So I'm going to say that factoring is not applicable. We don't need to do it, which is nice. It's already in simplified form. Our next thing that we need to find, we said, are our intercepts. So remember, our y-intercepts we're going to find by plugging in 0 for x. So we would have 2 times 0 minus 1. So we're going to get a negative 1 on top. And then we're going to get a 0 on bottom, which we're not allowed to have. So that means that there are not any y-intercepts. Then our x-intercepts are going to be the zeros of just the numerator. Remember that our denominator, when it gets set equal to 0, it's going to give us asymptotes. So we only care about where our numerator is equal to 0, which in this case is going to be at 1/2. Continuing on, remember that our next goal is to find our asymptotes. And we need to find both kinds. So we have our vertical asymptotes. We're going to set the denominator equal to 0. Well, x equals 0. And we're done. Pretty straightforward. We didn't have to factor or do anything else or solve. It's just x equals 0. And then our horizontal asymptotes. So notice that n equals 1, d equals 1, which means that we want to look at our leading coefficients, which are going to be 2 and 1. So 2 divided by 1 just gives us 2. So So let's go ahead and start plotting some of these things. So we don't have any y-intercepts. Our x-intercept is going to be at 1/2. We have a vertical asymptote at x equals 0. And a horizontal asymptote at y equals 2. Now, our last step, remember, is to make a table. So I'm going to go ahead and put my table over here so I have a little bit more room. And remember that we need to pick, they said, values before and after, and also in between any asymptotes or intercepts that we have. So we can kind of think about our x-axis as a number line, and we need to look at kind of the intervals that it's been broken into. So our first interval, notice, is going to be anything that's negative infinity all the way until we get to our first asymptote, which is at 0. So we can pick anything that's before that. So usually it's easiest to pick something like -1. Well, then we need to pick something that's in our next interval. And our next interval is going to be 0 to our intercept, which is 1/2. Which means that we need to pick a number that's in between 0 and 1/2. So we're going to go ahead and pick 1/4. That's a 4. Again, you can pick whatever number you want, but just make it easy on yourself. Don't pick something like 0.7258, right? That's not going to be super easy to plug in. So just pick a number that's easy. And then we're going to pick something that's in our next interval, which is just going to be everything that's after 1/2. So we can go ahead and pick 1. So then we're going to plug those numbers into our original equation. So notice if we did 2 times -1, we would get -2 minus 1 gives us -3, divided by -1 would give us 3. If we plugged in 1/4 and simplified, we would get -2. And if we plug in 1 and simplify, we would get 1. Again, if you need to use your calculator, you're always welcome to use that. And then we're just going to plot those points on our graph. So I have -1, 3, 1/4, -2. So I'm really close to my y-axis. And then we're at 1, 1. Now, we don't have a ton of points, but that's okay, because remember I said that those asymptotes are like black holes. So we know that as this side gets closer and closer, it's going to have to go up towards my asymptote. As x goes towards -infinity, it's going to have to go closer towards that horizontal asymptote. And on the other side, again, it's going to have to go down towards that vertical asymptote, and across and up towards that horizontal asymptote. And so that's going to be the general shape. You can always plug in more points if you want a more accurate graph. However, that's all that I'm going to ask for, is put 1 point in between and after and before each of our vertical asymptotes or x-intercepts. Alright, so let's look at another example. So this time we have f of x equals x squared minus 9 divided by x squared minus 2x minus 5. So our first step, remember, is to factor. And in this case, we can factor. So hopefully we see that my numerator can be factored to x minus 3. That's a 3 times x plus 3, because it is a difference of squares. Then our denominator, if I'm looking for what two numbers multiply together to give me -3 that add together to give me -2, it's going to be a -3 and a +1. So notice that we have a common factor of x minus 3. So those are going to get reduced. And so we're just left with x plus 3 divided by x plus 1. Now, for a little bit, we're basically just going to treat that as our new function. We're going to find all of our intercepts and asymptotes based upon that function. And then once we start graphing, we're going to come back to that factor that we reduced out. But for right now, we're going to kind of forget about it. So we want to find our intercepts next. So remember, for our y, we're going to plug in 0. For our x, we get 3 divided by 1, which gives us 3. For our x-intercepts, we're going to set the numerator equal to 0, which is going to give us x equals -3. Next up, we want to look at our asymptotes. Our vertical asymptotes first. Notice I'm going to set my denominator equal to 0, so we get x equals -1. For our horizontal asymptotes, we need to look at our degrees. And so notice that n is 1 and d is 1. So I just want to look at our coefficients. So we have 1 divided by 1, which is 1. So just like before, let's start graphing some of those things. So we have a y-intercept at 3, an x-intercept at -3, a vertical asymptote at -1, and a horizontal asymptote at 1. So then our final step is to make our table. Again, choosing our values that are before, after, and in between. So notice that my first 0 is going to be at -3. So we want to pick something that's before that. So let's say -4. Then we need to pick something that's in between -3 and -1. So let's say -2. And then we need to pick something that is after -1. Now notice that we could pick 0, but we've already had to plug in 0 to find our y-intercept, so we don't really need to use that one again. So what we're going to do instead, I'm going to pick 1, because it's going to give us one more additional point. And now you can either plug those numbers into your original function, or you can plug it into your simplified function. Either way, it's going to give you the same numbers. Your simplified function is just going to be a little bit easier. So if we plug in -4, we get 1/3. We plug in -2, we get -1. And if we plug in 1, we get 2. So again, needing to plot those additional points. And then using our asymptotes to know that they're going to have to get closer and closer to those asymptotes. Now, like I said, we were going to forget about that factor that we reduced out at the very, very beginning. So notice that that factor that we reduced out was x minus 3. So notice that if we set x minus 3 equal to 0, we would get that x cannot equal 3. And just because we reduced that out, remember that it's still a restriction for our function, which means that it's also going to need to be a restriction on our final function, which is going to cause us to have something a little bit different on our graph. So for our graph, usually when we have a restriction in the denominator, it gives us an asymptote. However, if we have a function where the factor reduces out, what's going to happen now instead is that it's going to cause a hole in the graph. And it's going to cause that hole at our restriction that got reduced out, which in this case is 3. So at 3, we're going to have a hole in the graph. So our graph would look something like that. Again, our x value still can't equal 3, but because it reduced out, it's not an asymptote, it's just a hole in that graph. Alright, and in our next lesson, we'll be going over our last type of asymptote, which are called our slant asymptotes.